Hello students, welcome back. We still have one more topic to go from section 1, and that is determining the sample size. Suppose that the weight of boys in a certain school district is normally distributed with a standard deviation of 3.0. Determine the sample size in order to estimate the mean weight within 1 pound with 95% confidence. We're looking for sample size. And where does the sample size show up in normal problem? Z is end minus center over SE. That's one formula that we have to know. And here's another formula that we have to remember. Standard error is sigma over square root of n. This one has a sample size. Standard deviation here is 3.3 pounds in this particular problem. So it's going to be 3.0 over square root of n. And that's something we have to put in right over here. And as for end minus center and so on, this thing depends upon the picture. So let's draw a picture. You see, I like this expression of z rather than x minus mu over something or mu minus x bar over something. There are so many variations. But the trade-off of this expression, n minus center over SE, is that it requires a picture. So let's draw a picture. Here's the outline. And then the best point estimate, x bar, is here, but this problem didn't tell you what that x bar is, so we don't know that. And then we have the left-hand side of that 95% confidence interval, and then right-hand side end of that 95% confidence interval. And this shaded part in the middle has the probability of 0.95 or 95%. So right here we have 0.95. Okay, that means the other 5% of the time I'm not going to succeed. And that's going to be shared by right-hand side and the left-hand side. Let's change the color. So 0.25, actually no, 0.025 is 2.5%. 0.025 here. Okay, that completed the picture. Now, how do we utilize this information here? We already used the standard deviation of 3.0 in the standard error formula, and eventually this will go to the denominator of this z-score formula. And how about the end? Well, I can use either left-hand side end or right-hand side end. Either way, it's going to be fine. Center, okay, that's the best point estimate S bar. The problem is I don't know any of those. I don't know either of these two. So looks like I'm in trouble, but not really. Even though I know neither what this L value nor what that X bar value is, I know L minus X bar or end minus center. You see? What is end? I don't know. What is center? I don't know. But what is end minus center? I know. The problem says it's 1 pound. What do you mean by that? We are estimating within 1.0. Well, this is my point estimate. And then within this confidence interval, we have allowed error. And that goes to the maximum up to here. and same over there. If it goes any beyond, then my interval estimation failed, so that's out of bound. So within this confidence interval, I can go only up to this much. That's within 1 pound. So end minus center, I don't know end, I don't know center, but end minus center, that one I know. So we end up with this. So Z is end minus center over SE, yeah? And that is, end minus center is 1.0. And then depending upon L minus the center or R minus center, I'm going to get either plus or minus, but this is symmetric, so I don't really have to care. Whether I put positive here, negative here, it doesn't matter too much actually. And the standard error here is 3.0 over square root of n. And that is associated to z-score for 95% confidence interval. Do you recall what that is? It's 1.96. To be a little bit more precise, you want to put plus or minus, but actually nobody cares plus or minus. And you can throw away the sign and do only just magnitude computation. And in the end, I have to take square to find out n value. So I don't really have to worry about pluses or minuses. You see, if you use this normal picture, especially with this symmetry, basically what we end up getting is sign mistake free. I don't have to worry about it. So, okay, we have an equation to solve. Can you actually get it done? Good question. I have to type something in, so I think I'll better stop here. So please record it or rewrite something because I have to get out of this drawing mode. And at that time, I'm going to lose all the information here. Okay? Okay, what do we have here? The visualization is like this. And then this radius is 1.0. So let's see. I didn't use the same method as I did over here, so let me just try to continue here. So z-score is end minus center 1.0 over SE 3.0 over square root of n. And let's increase the font so that you can read better. And that's approximately equal to 1.96, the z-score associated with 95% confidence level. Okay, how do you solve it? Well, multiply both sides by denominator. Then I'm going to get 1.0 is equal to 1.96 times the standard error, but standard error is 3.0 over square root of n. And I still have another denominator. Well, it's not a surprise. We have denominator over denominator here. I mean denominator of denominator, so things will be complicated. I knew that to begin with. So let's work out the denominator once more. Multiply by square root of n to both sides of equality. Then finally I'm going to get no denominator anymore. So multiply by square root of n to both sides. To the right hand side it disappears. To the left hand side I have that. And finally, divide by this. Well, dividing by 1.0, so actually that's nothing to it, but still, just for the argument's sake, let's divide by that. So we have 1.96 3.0 divided by 1.0, and that is, well, a certain value. Let's not worry about it yet. And that value is square root of n. In order to get n value, I have to square it, because square root of n is this quantity, so I have to square it. So n is approximately equal to the square of this quantity and that, well, let me finally take a calculator and then calculate it out. I'm getting 34.57 something. Now what do I do? If I get about this n value, then I can get the margin of error of maximum 1.0. But then again, we want within that 1.0, and this is not an integer, so I'd like to get an integer value that will ensure the margin of error within that given error bound of 1.0. So what do? We always round up. Even if you have 34.002, always round it up. We take n is okay. That concludes. And up to getting this equation, not too bad. We have this picture. Yeah. N minus center over SC, and SC is this. So plug everything in. Z-score, if you look up the table associated with 95% in the middle, or 2.5% there, or 2.5% there, or 97.5% there, no matter which way you look at it, it's going to be plus or minus 1.96, and nobody cares about pluses and minuses here because of the symmetry. So let's just put 1.96. It's okay to put negative 1.96, by the way, because we're going to square it anyway. So getting up to this equation is not too bad. Solving this equation here, if you're good at this kind of algebraic manipulation, great. But here in 1000 level statistics course, there are a lot of students who feel very, very lost about this kind of algebraic manipulation. And for that reason, I don't write this kind of problem very often. It's not that it's totally unimportant. It does have some importance. It's just that it's not anywhere close to confidence interval problem or confidence bound problem. So I rarely write it in the exam. I just say 10% or less. But it's not zero. Still, it does count something. And of course, in terms of my MATLAB exercises, there will be problems like that. That's one way to do it. Another way to do the same thing is to follow a bit more symbolic manipulation there. So n minus center is 1.0. So start from here, 1.0. So it's the end point here, whether it's here or there. It depends upon just pluses or minus, and nobody cares about it. Here I decided to use right-hand side endpoint. Okay, x bar plus the margin of error and minus x, so these two cancel out. So we get the margin of error, z times standard error. And then that turns out to be 1.96 times 3.0 over square root of n. What do we have? We have the same equation as before. And solving this equation, again, that requires some algebraic manipulation. We end up with this and then end up with that. Okay, that was the final topic. And that concludes session 1.